Okay, so now we understand that changing magnetic flux through a coil leads to an induced voltage. So, alright, that's great, but which way does the current go? We can figure out that the direction of the current by using Lenz's law. Lenz's law tells us that the current caused by the induced voltage travels in the direction that creates a magnetic field with flux that points in the opposite direction as the change in the original flux through the circuit. So what does that mean? The idea is that the magnetic field produced by the induced current is contrary to the change in the magnetic flux through the loop. So, contrary, think contrarian, right? You may have a friend who loves to argue and will just take the opposite side of whatever discussion you're having. So, induced magnetic fields are the same. So, to remember this, we can always think that if the magnetic flux increases through a loop, then the induced magnetic field will be in the opposite direction as the original magnetic field, so that way it's contrary to the original magnetic field. The loop is contrarian here, so it wants to point in the opposite direction. However, if the magnetic flux decreases, then the loop wants to maintain that same value of the flux, so the induced field will point in the same direction. So here we're going to start with an example. We have a loop of wire that has a magnetic field that is pointing up the page, and now the magnetic field has decreased. So that means that the flux going through the loop has decreased. So the contrarian loop wants to counter the decreasing magnetic field and induce a current pointing in the same direction as the original magnetic field. So decreasing flux means that we want the same direction as we started. So to induce a magnetic field that is pointing up, what do? Right? So original magnetic field is pointing up, the field decreased, so now we want to induce a magnetic field in that same direction. So how do we do that? Well, we bring back our right-hand rule, the second version, where our thumb points in the direction of the current and our fingers wrap around the wire in the direction of the magnetic field. So now it's kind of reversed. We want to make a magnetic field induced by the current that points up the page in the middle of the loop. So we grab the loop and make sure our fingers are pointing up on the inside of the loop. If we do that, we find that our thumb is pointing counterclockwise, so the current must flow through the loop counterclockwise. Alright, so we have a bunch of examples to do, so let's try that now. Okay, so now we want to try some examples with Lenz's law. So in our first case here, we have the south pole of a bar magnet is moving towards the center of a loop of copper wire as shown to our right here. So I guess we can do our demonstration. So we have our copper loop here, we have the south pole of our magnet, and it moves slowly towards our loop here. So what does that mean? Well, the first thing is we want to see which direction the magnetic field lines point. So if we remember here, if we are at the North Pole, that means our field lines are pointing out of the North Pole, and they are pointing into the South Pole. So that means that when we are visualizing this, that means that the field lines are pointing into the South Pole of the magnet. And so that means as we bring it closer to the wire, that means that the magnetic field lines are pointing out of the page and up towards the south pole of our magnet. So to work this out, the first thing we figure out is that direction of the magnetic field. So here it is pointing towards the south pole, so that means it is pointing out of the page. So now as we move that south magnetic pole closer to the loop, that means that we are increasing the magnetic flux, right? The field lines get closer and closer together as we move the magnet closer. So that means that the magnetic flux here will increase. So that means that the loop here, so this is going to generate an induced magnetic field that points into the page, right? So remember, if the magnetic flux increases, then that means that the direction of the induced field is going to be opposite. So that means that the field is going to point into the page. So that means if we want to induce a magnetic field into the page, how do we do that? we take our right-hand rule, and so we say, all right, well, I want the magnetic field to go into the page. So if I grab my loop here, that means my fingers need to point into the loop, into the page here. And in order for that to happen, my thumb here has to point clockwise. So that means that in this situation, the current, the induced current here, has to go clockwise. Okay? So yeah, so this takes a little bit of practice to do these, but you'll get plenty of practice. So yeah, so let's try a second one here. Okay, in this case, the north pole of a bar magnet is moved away from the center of the loop of copper. So we have our north pole, we move it away from the loop of copper, and so what happens here? Well, here our magnetic field lines are pointing out of the north pole. So that means here the magnetic field is going into the page, right? So the field lines are coming out of the north pole. North pole is above our loop here. And so what then, as we move it away from the loop of copper, as we move it away, then that means that the magnetic field here, or the magnetic flux, is decreasing. Right? So if you move it away, the flux is going to be decreasing because your magnet is further away. Okay, so now we remember that if the flux decreases, that means that the induced magnetic field, the induced B field, points in the same direction. So that means our induced field has to point into the page. And so now that we know it's into the page, now we pull out our right-hand rule again. And so now we want our induced field to go through the loop and into the page. And so once again, this time the induced current is going clockwise. Okay, and so now I've got a third example here. So in this case, it's a little different. So in this case, we have a magnetic field that is coming out of the page, and we have a loop of wire that is pulled to the right onto our uniform magnetic field. So what's happening here is we start out with no magnetic field going through the page. So our flux starts out to be 0, and then as the loop gets pulled to the right, now you have a magnetic field that is pointing out of the loop and out of the page. So that means that the original magnetic field here, so this is pointing out of the page, so that's our circle with a dot in it. And so here, the magnetic flux is increasing. It really goes from 0 to a pretty large value. So that means that our flux here increases. So if it's out of the page and increases, that means that the induced field is going to be in the opposite direction. So that means the induced current is going, the induced magnetic field is going to be into the page. And so if the induced magnetic field is into the page, then that means which direction does it go? Well, if it's into the page, then that means, once again, I picked an example that goes clockwise. So that was a little bit of a mistake there to do 3 that all went clockwise, since it's kind of a 50-50 shot here. But in any case, if the induced magnetic field was coming out of the page, then this would flip around, your fingers would point out of the page, and so then your thumb would point counterclockwise, and so that would then tell you the direction of the current. So in that case, it would be counterclockwise. All right, so these are tricky, so I think you're going to have to spend a bit of time practicing these, but in any case, you've got a bunch to practice here, so good luck with those.